We are going to be talking about tension test and the stress strain curve. This project is made by Giovanni Jean, Austin Stowquart, and Daniel Fitzsimmons. The stress strain curve is a chart that measures the stress and elongation of a material until fracture. Luckily, we were able to use such a device at SUNY Polytechnic last week.
How'd that get in there?
Allow me to explain what a tensile tester is. A tensile tester is a machine that measures and records elongation and force applied throughout tensile forces. To test a material, we need a strip and a dog bone-like structure. This piece is then loaded into a tension tester and is calibrated to ensure accuracy of the data. The extensometer is a device that we use to get more accurate location of fracture and displacement. It is attached to the specimen itself and does not impact the machine in any way. The machine will pull the specimen until it fractures, and we are left with data in regards to the force, stress, displacement, and elongation percentage. These are the results of the steel specimen and the aluminum specimen. It was measured in terms of elongation percentage and stress in MPa. These are the results of the steel specimen we tested. It is measured in terms of elongation percentage and stress in MPa. The shape of it is typical of metals. These are the results of the aluminum specimen we tested. It is measured in terms of elongation percentage and stress in MPa. This was also made in Edsel, similar to the steel specimen. Another part of our assignment was to choose a third element and draw a stress strain curve based on it. As a group, we chose titanium. It has similar application to steel, and so we found out the stress strain curve was also pretty similar. Now, in order to better understand the stress strain curve, I have drawn one. I marked several points of interest in green circles. I will now explain the first dot, proportional limit. This is the last point where the material is still in the elastic region, meaning it's the last traceable point where the material can return to its original shape. From this point, we are able to determine elastic modulus, or as it's also called, Young's modulus. Elastic modulus represents the resistance to elastic deformation. We determine this by rise over run. See the demonstration below. Another important point in the stress strain curve is the yielding point. The yielding point is where the material can no longer return to its original form. The common way of finding this, especially in metal materials, is having a 0.002 offset to the graph that is parallel with the original linear portion of the graph.
Is the highest point of stress that the material endures. At this point, necking starts to occur. Necking is where an area of the cross-section starts to decrease until it fractures. The tensile strength can be found at the peak of the stress strain curve, which is right here circled.
Ductility is the ability for a material to undergo plastic deformation. A material with a high ductility will be able to stretch a lot before it fractures. As you can see in the two pictures, the first one being steel it stretched a very large amount before it fractured, showing that it has a very high ductility. Percent elongation is found through the formula percent elongation equals length final minus length initial divided by length initial times 100%. Percent elongation is shown in both pictures by the increase in the length of the material from being stretched. And you can see that the steel was stretched out a lot more than the aluminum. Percent reduction in area is found through a similar formula where percent reduction in area equals area initial minus area final divided by area initial times 100%. And the area in question is the cross-sectional area, which is the spot where the necking occurred and the material fractured, which as the length of the material increased, the cross-sectional area decreases and it gets weaker and weaker until it fractures. The materials with high percentages in elongation and reduction in area are more ductile, as in the case of the steel.
Area under the curve up to the yield point, which is drawn right here on this image. The formula that can be used is 1/2 sigma y squared divided by E, where sigma y is the yield stress and E is the Young's modulus.
The toughness of a material is the energy that is required to break a unit volume of said material. It is the energy that is needed to break something. This can be found by taking the area under the stress-strain curve. This means it is the integral of the stress-strain equation. So the longer and higher the stress-strain curve goes, tougher a material is. Spider-Man is a superhero who uses webs like that of a spider. Unlike a spider, however, Spider-Man's webs are made of a polymer compound. Whenever he uses them, they are elongated from their initial position. This puts a great deal of stress on them. Take, for instance, the scene we saw in class, when he uses them to hold together a boat. The webs are being pulled from either end, just like the metal we used in the lab. This puts stress on the whole web and elongates it. It is exactly like the tensile test. Just like the tensile test, they will elongate until they pass the elastic modulus. Then, as the force is continued to be applied, they will begin necking. At that point, they can no longer recover from their damage. This is when they reach plastic deformation and the webs are permanently deformed. As the boat continues to pull on them, the webs will start to break, beginning at the necking point. They will no longer be able to hold the boat together, and it will begin to sink. So, Spider-Man's webs are very durable, but they are not completely indestructible.